afternoon, everybody. I hope that everybody can hear me well. My name is Justine Bonnot, and I am the future founder and CEO of the startup Quintech. I have a background in computer engineering and electrical engineering, and signal processing PhD. And Quintech is a work that is based on my research topic. So I'm going to present you this topic and a more general introduction. I have the Slack that is open on my other computer, so in case you have any question, I can see it on my other computer. So I apologize in advance for the very French accent, but I will try to do my best. So firstly, I will do a brief introduction about embedded applications and the topic of approximate computing. And I will then go into more details about finite precision arithmetic, which is the approximation that we consider in the Quintech project. And then I will present you Quintech, the tool that we have built, and a few results that we have obtained on this tool. So firstly, I guess it's not necessary to do the introduction, but I will do it anyway. So embedded systems are currently everywhere. So from your smartphone to your car and even in your toaster, their number has exceeded 22 billion in 2020. And this is a really huge market, which is going to exceed $110 billion by 2023. These systems are used to implement functionalities or applications. These applications are consuming energy. And to implement these applications, we have to embed code lines on these systems so as to pilot the electronics. Again, I will repeat it after, but of course, these systems are subject to several constraints, but I will come back to that later. Due to an increasing demand from users to get more sophisticated and complex systems, the number of code lines also increases. And this becomes a real challenge because you have to embed always more code lines on always more constrained targets. This problem is recent. For instance, you have only 10 years that are separating the car, the Chevrolet Volt, and the number that we have for the software of a current car today. So this is, in the case of the current car, it's yours or mine. It's not an autonomous car. It's a really classical one, and you have multiple by 5 the number of code lines that you have between those two cars, and currently in the software for a car, the number of lines is higher than 100 million. So of course, these problems are also going to intensify. The problem, so just to sum up, is to integrate embedded applications on constrained targets. I talked about that a little bit earlier, but the constraints can be multiple. It can be cost constraints, area constraints. Of course, if you reduce the silicon that you need to create your chip, you will then reduce the cost of your system. It can be also energy consumption constraints. And sometimes you want to work real time or to get an application that is really fast. So you can also have computation time latency constraints. But to do that today, so to put an application on a constrained targets, there are of course solutions in the industry because it's not a new problem. So these solutions are only in case it doesn't work from the very first time. So you take your application and you want to put it on your embedded platform, but it's not working. So it's too big, or it doesn't fit in your platform. So what can you do? So the first solution, and I call that bypasses. So you can pay for a more powerful or a bigger platform. So this is the first image. I took the image of a Porsche that is tracking a caravan, because you take a really powerful platform for maybe something that don't really need it. And this is the first solution. And the other one is to take the application and to try to work on the application. So in French, we say aux petits oignons. The goal is to really modify the application, maybe replace some parts of the application by approximation, so as to simplify it and be able to put it on the platform that you really want. Why do we need to do some bypasses? Because if you really want to optimize the application for your hardware platform, it can take a really long time. It can take between 25 to 50% of the total application design time. And it is currently generally done by engineers, so manually. And it can take up to a few months, for instance, in the automotive domain. In the end, when you do that manually, generally, your application is not optimized at the end, because you can only try a few configurations manually. And so you try an optimization version of your application, you try to put it on your platform, and you cross your fingers. And if it works, well, that's great. If it doesn't, you have to go from scratch again and to work on your application again. Our solution is to optimize your application. So it's just to face the problem, but of course we will have to do some trade-offs. The trade-offs, sorry for the writing that is not on the right place, is to do a slight degradation of the quality. So it's already done currently in a lot of systems, so it's not new, but what we want to do is to explore this trade-off more intelligently with our tool. And this is called approximate computing. So what we do is to do a trade-off between the implementation cost, the performance of the application, and the quality of the output of the application. So you will allow some errors to occur in your application, and the goal is really to manage to control these errors and to tolerate them only in parts of your application where they won't damage too much the output of your application. So just a really simple example to understand what we do is if you put a lot of energy to do your application. So in this case, the application is to reproduce Mona Lisa. If you put a lot of energy, then you have a really high quality version of your Mona Lisa. If you put a really low energy to do your Mona Lisa, you will have a really low quality. And in the end, you won't even be able to use the output of your application. And so the goal of approximate computing, to use it in industry, is to really find the good trade-off between both drawings to be able to use the output of the application and that the user doesn't see the difference between a classical version with a really top quality and your version. The problem is when you do approximations in your application, so you can do approximations almost everywhere in your application. You can replace a lot of things, even replace arithmetic operators. So you have a lot of places where you can put approximations. So this is a first thing to explore. Another thing is that you can also fine-tune almost every type of approximation that you will put in your application. And so you have a really large design space to explore. And this is why automated tool can really be useful to really use that in industry. So now I'm going to really focus on the approximation technique that we really focus on Quintech. But in case you want to discuss a little bit more about the other techniques, we can also talk about that after the talk if you want. So what we really consider in Quintech is a data level approximation. So you have several levels of approximation. You can do approximation on the hardware or computation level, but here we are interested in modifying data. So you can take data and modify the accuracy of the data. So this is finite precision. what we will talk in the rest of the talk, or you can modify the number of the data that you will use. This is downsampling techniques, or you can use maybe less up-to-date data. In case of finite precision arithmetic, so you modify the accuracy of your data. Here we will consider only fixed point arithmetic, but in our tool we also can use it for floating point arithmetic or custom floating point. But for fixed point arithmetic, the goal is to replace all the floating point data in your application and to replace them by integers. So to be able to represent data with a comma, I don't know how to say that in English, but a real number on an integer, you will have to do a conversion process. So you have two steps in this conversion process. The first step that will allow us to determine the number of bits that you will require to represent your integer part. So all the pink part and the yellow part is a sign bit. The pink part before the comma is the integer part, so just to represent everything that is before the comma, and it is determined by the data dynamic range. So here, if you don't find the really right number of bits to represent your data, you will maybe have overflows that can occur, and this can be really disastrous for your application. And then after the comma, you have remaining bits. So that will be here to represent the accuracy on your data. This is the fractional part, and here you will be able to do a trade-off. So not on the pink part, but on the blue part, you are able to maybe remove a bit, remove several bits, but you have to check the impact of doing so on the output of your application. So you have to solve an optimization problem, because what we want to do to really benefit from fixed point arithmetic is to select a particular word length for each variable. So each variable will have its own data type. And to do that, you will have to analyze the impact of each word length for each variable on the output quality, but also on the performance, on the cost, on the implementation cost of your application. So the problem that you have to solve is to minimize the implementation cost of your application, depending on the vector of approximation sources. So in the case of fixed point arithmetic, this vector is the vector of word length. But you have also to control that your quality won't be too low, depending on an accuracy constraint that has been given by the user. So you have to measure each time you try an approximation vector, you have to measure its impact on the degradation of the quality. And this optimization problem, it can be really, really long to be solved. Indeed, the evaluation time for this optimization problem will depend on the time you need to evaluate your application in fixed point and in floating point on a single sample, input sample. Generally, you don't do that on a single input sample. So it depends also on the number of samples that you consider are enough to get a good enough estimation of your accuracy output of the application. And of course, it depends on the number of times you want to evaluate the metric, so the accuracy metric. For instance, we have worked on an image processing application, and just for the simulation of the image processing application in fixed point on a single image, it took 40 seconds. So it can be really, really long, because in this case, you had 50 variables to optimize, so it's a really big problem to solve. And this is why we have built a tool to help people trying to solve this problem. So what we build is a solution, an automated software tool to help you optimize the data arithmetic of your embedded applications. It allows reducing the development cost of your application, because we remove a manual part. We help engineers, so we help them going faster on this part. And we also allow reducing the area and energy consumption of your applications between 20 to 40%. Of course, this is an average figure, so it has been obtained on a few image processing applications, but I have also some figures on FFT, on a Cholesky benchmark, and on other benchmarks. It really depends on the application and on the constraints that you give. So if I take the development chain of an application for an embedded system, so the first step is to design your application with a high-level language. So here I put MATLAB, but it can be C, C++, Python. So we are only compatible with C, C++ for the moment. At the output of this step, you get a legacy code in floating point generally, because you only want to check the functionality of your application. And then if you go a step further in the development chain and you go to the hardware synthesis part, so this chain is for FPGA implementation, you can use tools as HLS, for instance, as Vivado, to help you translate your code into a code that can be understandable by the hardware platform. But you won't go directly from the legacy code up to the optimization, up to the hardware synthesis block. You have to put an optimized version of the code to benefit really from the hardware platform. And this is where you can use Quintech. So we are really here to optimize the legacy code and provide a code or for the HLS tools, or directly for a DSP or a microcontroller. The flow of our tool, so we have a user interface, but you can also use it in a command line. And then we have two main parts in our tool. So the first one is the insight block. It allows us determining some information on the application, on the variables. What we take as input, it's C, C++ source code, as well as build and execution scripts. And in this block, we determine the complexity of variables. We can talk about that later if you want. The extrema of each variable, and the distribution to see where the data are concentrated. And in the end of this step, we also determine the integer word length. And after, since we have solved a part of our problem, because we have all the integer word lengths for each data in the application, then you can go to the optimization block, where you will have some accuracy evaluations and word length optimization to get the optimized version of your application. The tool flow, just to go in more details. The first step is to go in a source-to-source compiler that will analyze your application code, determine if some data types have to be identical to others. So we call that unified data types. I can also talk about that later if you want. And also to modify some inputs of the function that is going to be converted in Fixedpoint, the output also, and to generate the source code of the application with virtual data types to be used then in the integer word length determination and word length optimization. Then in the first block, so you will we will log the data, simulate, log the data, determine the integer word length, and then do the optimization. And in the end, you get the Fixedpoint application source code, or with data types that emulate the Fixedpoint arithmetic, or with the shifts that are included in the code to be embedded on a DSP or a microcontroller, for instance. So this is a video just to show you quickly the application. When you
open our software tool, you can find all your projects on the navigation tab on the left. A first compiling step allows extracting a few information about your code. A second source-to-source building step allows the extraction of information on your application. For instance, you get information on the range of the different variables of your application as well as their complexity. Everything is written down in this table with the minimum values, maximum values, and the complexity in terms of number of operations for each variable of your application. You can compare your original code with the version that is generated by the source-to-source compiler with the different files that you have in your code. You can create a new optimization configuration with the name of your configuration, the noise constraint, etc. In the end, you obtain, according to your noise constraint, trade-off curves with the optimized word length of each variable in your application.
Figures on FFT. I will go really quickly on that. No, I don't read. I have just seen a question on Slack channel. So just a few figures on the other benchmarks that we have worked on. So on an FFT, we have optimized an FFT using an accuracy constraint of 77 dB of SNR, and we have so obtained a few optimization curves, but this we should go more into details to discuss about the optimization process. We can do that after if you want. So this is some optimization curves, other optimization curves, but the results here are more interesting. So the Fixedpoint implementation on 77 dB. So these figures have been obtained compared to the original code in floating point. I guess it's on an ultra scale plus. And so we can divide the total dynamic on-chip power by 3.6. And what is the most interesting figure is that we divide the number of DSP blocks by almost 8. So again, I have other figures if you want to discuss about that. Quickly about the time of our tool, it takes on this example and just on a single input vector 45 minutes. So it's really long, and it's the reason why we have worked on other techniques from my PhD thesis that we have included in the tool, but they have not been used for these experiments. So we can also discuss about that. But I just want to leave a little bit of time for questions. So I thank you all for being here and attending the talk, and I'm here to answer any question. I will just put my glasses on to check the Slack channel.